Greetings, this is Purple Target. Welcome to my foray into a KSP Let's Play. This is Krash Test Kerbals, Episode 1, Tack 1, What One Fool Can Do, Another Can. Currently using Kerbal Space program version 0.18.2 from Squad. And like other videos about how to play KSP, it will be about how to build and fly these monstrous and rather terrifying contraptions to hurl hapless Kerbals into the cold black emptiness of space, to the sound of soothing ambient music. Now, I came across KSP when I was mulling through Kurt J. Mack's Minecraft videos, which I did find very informative and entertaining, and great for keeping track of the development of the game until it matured enough that I was interested in paying attention to it. However, unlike Kurt, I don't have the patience of a saint. I get bored with too much trial and error, so about 30 minutes after starting the game, I decided I wanted to know if I had the fighting chance to make it to a destination before I tried launching. Boy Scout motto, be prepared, all that kind of nonsense. So I started doing calculations for myself. So I don't really see much value in me replicating tutorials or gameplay vids like how to dock and how to turn and how to transfer fuel or use the UI or stuff like that. There's lots of folks making those kind of videos, and they're doing far better than I could. So if I'm going to spend any time on this, I want to do something different. So on the forum before Christmas, there was a post that got my attention from some 14-year-old complaining that math is hard. Now, I've seen this sentiment repeated by others frequently, which is a little depressing, and it is also complete nonsense. What one fool can do, another can. So the mission for this Krash Test Kerbal series is going to be to play KSP and discover that math isn't hard. Ignorance is. Math is just a tool, and if we have the willingness to hone it and learn how to apply it, then we should do well. So, in order to do that, while we're playing KSP, we're going to explore some of the science and learn some of the math and discover some tools to make some of these parts a little easier in an attempt to make sure that we can get our Kerbals to our destination in one piece. And then they're going to do... and then, of course, profit. You know it. Alright, so today's objectives are pretty short, so we'll carry on with figuring out thrust to weight ratio, or how to get off the launch pad. Alright, got KSP flashed up here, so we'll get started. Get a new game. Krash Test Kerbals. And we'll get started with our build. Alright, so for this build, we're going to have to keep track of a few items. We're going to have to keep track of the total mass, and the dry mass, and the thrust of any engines that are going to fire at the same time. So the simple case, we'll start with a state Putnik for total mass 0.05. Nice and light. And we got a big fuel tank. So the Rock Max 2 X200, 4.5 tons loaded, 0.5 tons dry. So that gives us 4 tons of fuel. Put that on there. And for an engine, we'll start with the LV909. That's half a ton and a thrust of 50 kilonewtons. I'll put that on the bottom. And we're going to have this sitting on the launch pad a bit to thrust away, so we don't want it running away on us. So we'll get some of these struts, and they're 0.1 ton each. We got 3 of them for 0.3. There we go. And we'll get some of these RTGs so that the probe doesn't run out of power. They're 0.175 each. I'm going to put on 2 of them, not because we need them that many, but it will round out the number, so it'll be 0.35 tons for both of them. And that brings us up to 5.7 tons total and 1.7 tons dry with a thrust of 50 kilonewtons. Looks kind of like the robot from Heavy Metal, doesn't it? I think it does. Heavy Metal Robot 1. Let's get the action groups, get the gears down properly. There we go. Okay, so that's our design. We'll take it out to the launch pad and we'll see what we can do with it. Get the gear down. There we go. So to answer the question of if we're going to lift off the launch pad, we have to take a look at our thrust-weight ratio, which is the thrust of the engine divided by the weight of the spacecraft. The weight of the spacecraft is simply the force of acceleration of gravity on the spacecraft, which is equal to the mass times the acceleration of gravity. This is usually indexed off of one standard gravity, which is 9.8 meters per second squared, or whatever the gravity at sea level on Kerbin is. So the thrust-to-weight ratio, when we put those together, equals the thrust divided by the mass of the spacecraft divided by times the acceleration of gravity, which equals 50 kilonewtons divided by 5.7 tons times 9.8 meters per second squared, or 55.9 kilonewtons, and we end up with a ratio of 0.89. Now 0.89 is less than the ratio of 1 that we need to take off. The ratio has to be greater than the local G's, which is 1 on Kerbin. So this is not going to take off as it stands. Now if we flip the equation around, we can look at the mass that the engine can lift as being the thrust that the engine produces divided by the thrust-weight ratio of 1, or possibly less depending on if we are looking at a different planet, times 9.8 meters per second squared, or we can round that to 10 just to make it easy. We have 50 kilonewtons divided by 10 meters per second squared, and that'll show us that we can lift about 5 tons with this particular engine.
10, 9, 8.
So in order to get our thrust-weight ratio up to 1,
4, 3,
we need to
2,
burn off some
1.
fuel and lighten our load or mass of our spacecraft by about 0.7 tons. That'll mean about burning off around 20% of our fuel. And at that point, the spacecraft should lift off the pad. I'm starting to see some movement.
Liftoff.
And there it goes. Now, the spacecraft will continue to accelerate as it keeps burning fuel and it gets
Clear the
lighter. That thrust-to-weight ratio is going to improve, and it's going to increase the acceleration of the spacecraft. Now, the thrust-weight ratio is related directly to the G's, so 0.89 thrust-to-weight ratio can't take off on Kerbin, but it would be able to on Tylo or Lathe, where the surface gravity is 0.8 Gs, or 7.85 meters per second. And as the probe continues climbing in altitude and burns off the rest of its fuel, it'll again continue accelerating up to the maximum, where it's only the dry weight of the spacecraft. So our maximum thrust-to-weight ratio is going to be equal to the 50 kilonewtons divided by 1.7 tons, so our dry weight, times 9.8 meters per second squared. And that will come out to a ratio of 3.0. So at this point, there's not much else to say with this flight. HMR1 is going to carry on going in a decidedly upwards fashion until it runs out of gas and come down. And there's not much else about thrust-to-weight ratio I need to talk about with this particular design, so this gives us a chance to chat about something else. Now, the phrase that we named this episode after, that what one fool can do, another can, is actually an ancient Simian proverb, and came out of a textbook whose prologue follows on the very subject of calculating. Considering how many fools can calculate, it is surprising that it should be thought either a difficult or tedious task for any other fool to learn how to master the same tricks. Some calculus tricks are quite easy, some are enormously difficult. The fools who write the textbooks of advanced mathematics, and they are mostly clever fools, seldom take the trouble to show you how easy the easy calculations are. On the contrary, they seem to desire to impress you with their tremendous cleverness by going about it in the most difficult way. Being myself a remarkably stupid fellow, I have had to unteach myself the difficulties, and now beg to present my fellow fools the parts that are not hard. Master these thoroughly, and the rest will follow. What one fool can do, another can. So this prologue is from a fellow named Silvanus P. Thompson in his book, Calculus Made Easy, and he wrote it back in 1914. So apparently not much has changed in 99 years. The average calculus textbook these days is probably still weighing in at 650 pages of dead trees, whereas Calculus Made Easy, somewhere between the size of a Three Investigators novel and a Hardy Boys softcover.
Flame out.
The other thing that hasn't changed in 99 years is the underpinnings of calculus. And so the good news there is that Calculus Made Easy is public domain and available online through the Gutenberg project as well as elsewhere. I'll put a couple links below, or you can look it up on Wiki. If you're going to take calculus anytime in the near future, I'd suggest checking it out. I should probably throw in some obligatory disclaimers. I'm not a rocket scientist, far from it. So, someone like Scott Manley contradicts something I say, take his word for it. I will. Also, before you get too terrified about me leading off with a quote from a calculus textbook, I don't actually intend on using calculus if I can avoid it in this series. I was never really that good at it in university. I'm certainly not authorized to try and teach it. I also don't intend on being overly precise. It is a game, so it should still be fun. I want to get to quick calculations or methods in order to get answers. There'll be some head cheese math, etc. I'm not going to be fussed over significant digits. I'm going to introduce a lot of rounding errors. I'm going to use very approximate numbers. And fortunately, as simulators go, KSP is very forgiving. So I'm just looking for answers to get us in the right ballpark. And the mantra there will be close enough for government work, and we'll move on. I'll also note that I haven't actually been playing the game that much. I probably logged more time making spreadsheets and studying and calculating than I have playing the game. So there should be plenty of opportunities for engineering failures and crashes and massive explosions in the proper Kerbal fashion, since even if I get the math right, I might still suck as a pilot. So I'm looking at the altitude still climbing here, and I gotta say I'm kind of impressed with our little LV909 on the probe here. I really wasn't expecting to break Atmo until second or third episode. For something that I wasn't able to get off the ground, it's doing pretty good. And there's our apoapsis at 145, 917. It's not bad at all. I think I'm going to have to reevaluate the 909. I can see why people use it on landers a lot. Okay, there's also a couple of assumptions that I'm going to make for the series. First is, Kerbals are going to be safe anywhere on Kerbin. I'm not going to do rescue missions to get them out of a desert or off a mountain. I figure they can call a cab. Just because we can't see it doesn't mean they're not there. Another assumption I'm going to make is that crude pods are going to contain all life support requirements for an indefinite stay in space. Until the game changes otherwise, I'm not going to worry about Kerbals running out of life support if they're safely in a pod, even if they're on a remote planet, for an indefinite period waiting a rescue or other evacuation to back to Kerbin. Alright, my last assumption has to do with you. I'm going to assume that you know a few of the basics, like how to do math, order of operations, some basic algebra, so that if I give you a formula you can figure out how to plug in your numbers. I'm going to figure you know how to use a calculator or spreadsheet. And if you don't know what the hell I'm talking about with a particular term, then I'm going to assume that you can access the infinite knowledge of the internet through Google or Wiki. And since you're here watching this one, I'm going to assume that you know how to find other KSP gameplay videos on YouTube or Twitch in order to fill in any blanks that I'm missing. As I said, there's lots of other videos out there. And I assume if you're watching this that you're interested in either learning or entertainment. Don't know how the latter part's going to work out, but if you're looking for learning, then you'll need to do the work. I'll try to show you the calculations required, but it's only a piece of the puzzle, and it's up to you to put the rest of it all together. So just as a review, our thrust to weight ratio equals the force of thrust for the ship divided by the mass of the ship multiplied by the gravity. That'll give us a ratio to compare against standard G's. Or we can use the gravitational force of the body that we're working on. So if it's lathe or Tylo, we'd use 7.85 meters per second instead of 9.8. And that will give you a ratio for that planet. The other thing that we can figure out is our thrust divided by 10 will give us an approximation of the mass that we can lift off the pad at KSP. and thrust divided by 20 will give us a mass that an engine can lift into orbit off of KSP. That has to do with the optimal thrust ratio being around 2 times the surface gravity for the planet that we're trying to take off from. And we'll get into that, or the reason for that, next time when we discuss drag. So for Kerbin, we would stick with a thrust weight ratio of 2, and if we were looking at lathe or Tylo, where the gravity is 0.8, we'd double that, and we'd be looking for a thrust weight ratio of 1.6.
Splashdown. Negative contact.
Alright, so now let's take a different engine that doesn't need to sit around on the pad the whole time. We'll take off our LV909 and we're going to replace it with Poodle. So this one weighs 2.5 tons instead of 0.5, so it's going to add 2 tons to both the dry weight and the total mass. And it's going to change the thrust quite a bit. We're now at 220 kilonewtons instead of 50. Call it number 2 and take it to the launch pad. And there we go. So the other way to solve the problem is to see if the force generated by the engine can accelerate the spacecraft faster than the force of gravity can bring it down. So using the equation of force equals mass times acceleration, we can switch that around and find the acceleration for the spacecraft is equal to the force of thrust of the engines divided by the mass of the spacecraft. So now we're at 7.7 tons, so our equation A equals F over M be 220 kilonewtons divided by 7.7 tons, and we get an answer of 28.57 meters per second squared. And as long as that's greater than 9.8, then we can take off at 1g. In fact, if we divide it by a standard gravity of 9.8 meters per second, then we end up with an acceleration of 2.8 g's.
8, 7,
So
6,
this will
5,
not only take off
4, 3,
the launch pad,
1.
but it'll do so
Mark.
roundly.
Liftoff. Clear of the tower.
There she goes.
Look at that sucker go!
Now the actual maximum acceleration for this will be 220 kilonewtons divided by the dry weight of 3.7 tons, and that gives us 59.46 meters per second. We divide that by 9.8 meters per second squared for the standard gravity, and we end up with 6.1 Gs. And we might also notice that the equation that we ended up with, F over mg, is actually pretty much the same as what we saw before with the thrust to weight ratio.
Flame out.
Just so you know what to expect, there's certain constraints and restraints I plan on using for this series. First is plan on using vanilla KSP stock parts, no mods, including McJeb. At least I'm not intending support. Yes, there's mods and tools that can do all these calculations for us, but then we're not going to learn and understand what it actually means and how it works. My design philosophy in building rockets is going to attempt to minimize debris, maximize reusability. Figure it's just good practice for career mode. And when we send Kerbals up, we're going to go with the assumption that they must eventually come down. That is, if at all possible, we're going to give them the means to get back to Kerbin. And as much fun as it might be to try to get Jeb to sweat, I'm not actually out to kill any more Kerbals than might meet unfortunate ends in the normal course of such a dangerous activity as exploring outer space. And I will try to avoid game-breaking bugs if we can at all avoid it, like the RCS bug from 18.1. It's one thing to show proof of concept, but a can of hairspray shouldn't get a probe anywhere other than a hair salon. The main point of these is that we don't actually learn anything from exploiting game-breaking bugs. So the other method is a straight up calculation of the acceleration of the spacecraft being equal to the force of thrust of all the engines divided by the mass of the spacecraft. And that's going to give us our acceleration in meters per second, which we can then compare against the acceleration of gravity of the body that we're on. So if it's greater than 9.8 on Kerbin, then we can get off the launch pad. If it's greater than double that, 19.6, rounded up to 20, then we can probably ascend into space using that acceleration. Similarly, for looking at other planets, again, Lathe and Tylo, where the acceleration of gravity is 7.85, round it up to 8 and double it for 16, and we should have enough thrust to get into orbit from those bodies as well. So there you go, a couple different methods of calculating thrust-to-weight ratio, and with that we should be able to get off the launch pads and carry on with the next topic. So I think that's enough foolish nonsense for a first episode. If you've learned something or had fun, or if you think that there's value to this series, then go ahead and subscribe, thumbs up, leave a comment, tell a friend. I run on positive feedback. If there's interest, I'll carry on trying to do these.
Splashdown. Negative contact.
This is Purple Target at Crash and Learn. Peace out.